Now that we've discussed how we can structurally model digital circuits, or in other words, describe the schematic or structure of a circuit in text, let's talk about some other ways that we can also describe digital logic using hardware description languages and computer-aided design tools. Another style we use for describing hardware focuses on describing the functionality of the hardware and can be divided into three abstraction levels. The highest level, the most abstract level, is the behavior description, behavior model, which we can then put down to a lower abstraction level, the register transfer level, or RTL, which we'll talk more about later this quarter and also into CPE EE233. And then from there, we can convert this down to the gate level, which is at a level much closer to the actual devices in our hardware. So at the highest level, we can describe the behavior or the algorithm of the piece of hardware that we'd like to implement. But note that this has abstracted many of the details away from the hardware. So we have to be careful here to make sure that we're actually designing the hardware that we'd like to get at the low level. Many times at the early design phases, engineers will use behavioral modeling for testing simulations and then use other lower level abstractions as the design is developed. The register transfer level describes how data flows between state elements, and we'll talk more about this later as this is an important abstraction level. And at the lowest level, we have a net list of primitive gates. Now, engineers usually design hardware using a variety of these styles, including structural modeling. So now let's talk a little bit about how we can do behavioral modeling in Verilog. So first remember that inside our Verilog modules, we can include the wire data type, which can also be a vector. And I can use continuous signal assignments to assign values or connect these wires together or connect wires to outputs. Another part of the Verilog language are procedural statements. And procedural statements are included in either one of two different types of blocks. Initial blocks, which we've seen already in our simulations, or always blocks. Each of these have a begin and an end statement to tell the Verilog synthesizer where the block begins. Semantically, the initial statement will occur only once. Now the always block, just like the other continuous signal assignments and other block instantiations that I make inside my module, occur in parallel with these other statements outside. However, inside the procedural statements inside of my always block have sequential semantics, meaning that they are essentially evaluated one at a time. After the always, I have the @ symbol and then parentheses, and I list input signals that when these signals change, trigger the reevaluation of everything inside this always block. Okay, so I have three procedural assignments inside my always block here. In my sensitivity list, the inputs that are going to trigger if they change the reevaluation of this always block, I have A and B. So whenever A and B change, I'm going to reevaluate these statements. So the order of these procedural statements do matter because they are essentially evaluated sequentially. And I have one more thing to note here. The left-hand side of my procedural assignments have to use a different type called RAG for reg. This does not necessarily mean that this symbol will be instantiated and synthesized as a register, which we'll talk more about later, but this is required. The left-hand side, the signals on the left-hand side must be defined as the reg type. Now, Verilog also has a nice feature where if I don't want to list specifically the signals, I can include the star symbol here, which will automatically include in the list all of the signals which are read in the always block. This can be useful when I want to ensure that I'm creating combinational logic with an always block or this high-level algorithm description. Okay, let's do a more concrete example using a behavioral model. Let's say I wanted to create a combinational circuit for my sandwich example that I previously used. So my sandwich could either have ham, salami, or bacon, and it was only valid when the sandwich either had ham or only salami or only bacon. And the expression for my sandwich looked like this. So now if I wanted to create a Verilog behavioral model for this, Okay, so in my always block, I'm going to have this be reevaluated whenever the inputs change, because essentially these are the inputs into my circuit that I want to design. So when ham, salami, or bacon change, the logic inside this block will change. I'm also going to need a register type so that I can assign this inside my procedural statement. And I'm going to go ahead and assign the output V, connect that to this valid signal. Okay, so now let's describe from a high level what we want our sandwich checker to do. And so here what I can use, and so now I'll use something that looks similar to what you may have seen with a high level programming language, which is an if statement, where I'll say if ham is equal to 1 and salami is equal to 0, and so here I'll use a logical and in this if statement. So if salami is equal to 0 and bacon is equal to 0, then my valid signal, the sandwich, is valid. So if I have the inside of an if procedural statement that has more than one line, I can also signify this with the begin and end. But in this case, because it's only one line, I don't need those. But what I will need to do is describe the other cases. And so I'm going to say else if ham is 0, the sandwich has salami, but doesn't have bacon, then the sandwich is also valid. And then the third type of sandwich that can be valid is if it has only bacon. Now there's one more thing I need to do here, and that is describe the default case, because I want this to be combinational logic. If none of these conditions are satisfied, then I want the sandwich to be correctly identified as not being valid. So I'm going to describe the else case. All other cases, valid will be 0. So now we have a behavioral model for our sandwich checker, which we had previously described using a direct gate level implementation and a continuous signal assignment. Note that although I described it using these higher level constructs, the synthesis tools, assuming I don't have any syntax errors in my description here, will ultimately synthesize the same piece of combinational logic.